Hi everyone and welcome to the channel. Today we're diving into 11 C++ habits that even experienced developers frequently fall into. Number 1. Template metaprogramming without constraints. Unconstrained templates lead to cryptic error messages when instantiated with incompatible types. Here, type T might not have normalized method. Modern C++ concepts and constraints provide clear compile type validation and dramatically improve error messages. Using them will make you enjoy template programming. Number 2. Misunderstanding move semantics. Explicitly using std_move on function return values actually prevents return value optimization. When returning local variables, let the compiler handle the optimization. Number 3. Thread-unsafe singleton implementation. The double-checked locking pattern is notoriously error-prone. The thread safety problem with this implementation occurs in a multi-threaded environment. Imagine two threads A and B call getInstance simultaneously when instance is still null. Thread A checks if instance is not null and sees that it's null. Before thread A can execute instance is equal to new singleton, thread B also checks if instance is not null and also sees that it's null. Both threads will then try to create a new instance. This results in two instances being created, violating the singleton principle. Whichever thread sets instance last will win, and the earlier allocation will be leaked. Since C++11, static local variable initialization is thread safe, providing a much cleaner singleton implementation. Number 4. Raw, new and delete in modern code. Even if you implement the rule of 3 or 5 correctly, direct memory management is error prone. Embrace the rule of 0. Let smart pointers and standard containers own resources. Number 5. Hidden temporal coupling. Here the class has two methods that must be called in a specific order. First, call configure to set up the connection, then call open to actually open the connection. However, nothing in the code enforces this ordering. A developer could easily write something like this. This is called temporal coupling, a dependency in the correct sequence of operations that's not visible in the API design. It's hidden because you would only know about it by reading documentation or worse, encountering runtime errors. The second implementation uses the type system to make it impossible to call operations in the wrong order. The connection class no longer has an open method. Instead, it has a configure method that returns a new type, configured. The configured class has the open method. The configured constructor is private with connection as a friend class. Hidden temporal coupling creates maintenance nightmares. Use the type system to enforce correct call sequencing. Number 7. Improper forward declaration. Forward declarations reduce compilation dependencies but are misused when attempting to use incomplete types. Understanding when a complete type is needed prevents subtle compilation errors. Here's what's happening. We forward declare foo, making it an incompatible type. We define a function process that takes a pointer to foo. The problem is that inside the function we try to call do something on the foo object. This fails because the compiler only knows that foo exists but doesn't know what method it has. The better approach is forward declare both foo class and the process function in the header. Include the full definition of foo in the implementation file where the function is defined. Number 8. Failing to account for exception safety guarantees. Code should provide at least the basic exception safety guarantee. Operations either complete successfully or leave the program state unchanged. Strong exception safety often requires copy and swap idiom. In this code setting, the height might throw an error and might leave widget in an undefined state. The copy and swap idiom ensures the swap is only performed if no exceptions are thrown. Number 9. Using std_bind instead of lambdas. std_bind creates complex types that obscures the intent and cause unnecessarily verbose error messages. Modern lambdas are more flexible, clearer, and often more efficient. Number 10. Violating the rule of special member function. If you define or delete any of the special member functions, you would likely need to handle all 5. Better yet, use smart pointers and follow the rule of 0. Number 11. Non-virtual destructors in base class. If a class has virtual methods and is meant to be inherited from, it must have a virtual destructor. Otherwise, deleting a derived class object through a base class pointer results in an undefined behavior. When you delete a pointer in C++, the language determines which destructor to call based on, number one, the static type of the pointer, what the compiler sees at compile time, and number two, whether the destructor is virtual or non-virtual. With a non-virtual destructor, only the destructor matching the static type is called. With a virtual destructor, C++ uses dynamic dispatch to call the correct destructor for the actual object type. If you found this helpful for improving your C++ skills, consider subscribing for more in-depth programming content. Leave a comment with questions or your own experience with these issues. Thanks for watching, and I will see you in the next video.